Hi everybody, I'm Adrien Vergé. Gosh, another French guy in this conference. I'm going to present this presentation called Hardware-Assisted Software Tracing. And this talk presents some research results led by Polytechnique Montreal and LTTng. Basically, it will introduce some very useful and widespread tracing hardware that is on your chips now from ARM and Intel. And it will demonstrate how good tools can improve your software performance and how easy it is to use it. So this talk is about tracing. Doesn't seem to work. So this talk is about tracing. We are going to talk about tracing and more precisely how to improve tracing by using hardware, how hardware can be used to enhance it in terms of reducing overhead and having less footprint. So in this presentation, we are going to present tracing, precisely software event tracing, then show hardware capabilities, and then the improvement that we made that use hardware and try to enhance tracing. First, what is tracing? My definition, it's a technique to see what is going on in your system, so to see under the hood, and to trace a process, a whole system. It can record a lot of different events, and can be used to debug a wide range of bugs that are otherwise extremely challenging to debug. For example, it can be performance problems in complex parallel systems or real-time systems. So it's recording events to see under the hood. So we record events during software execution. This can be kernel events from hierarchy handlers, system calls, scheduling activity. It's already enabled in many places in the kernel, and it tells you what is the system doing during the execution. It can also be trace points in user space at strategic places that you choose in your program in order to debug it. And why recording events? By recording these events, you can answer many questions. For example, why is your software crashing? Where are the bottlenecks? How to improve performance? And save crucial resources for embedded systems like memory, time, and battery. Let's see an example. Just to settle the ideas, we are going to trace a program, a simple program with LTTng, which is a performance-oriented tracer, software tracer. And we're going to see the results and see what we can do with tracing. Here is our example. It's a really simple program that launches 2 threads. The first thread will produce data, and the second one will consume it. For example, a video stream that is produced by a first thread and then consumed by another one. We trace this program, so we record events, and then we analyze it. And here is what we can see. For example, this is a view of TMF, the Tracing and Monitoring Framework. It's a plugin for Eclipse that show you the tracing results. You have different views here. For example, at the top, you see the timeline with the parent thread and the 2 child threads with different colors. Green is means the thread is executing on CPU. Blue is syscall. And yellow is when it's blocked by something. For example, we see the parent thread is blocked all the way long till the end of the execution because it waits for the child thread to finish. You also have views of resources. Here you have CPUs, which CPU is currently running or idle. You have IRQs. You have many information thanks to tracing. If we zoom at the beginning of the execution, we can have very detailed information Here we see the first thread does an execvio syscall, then lots of memory allocation. It's running, and 2 clone syscalls to launch the 2 threads, but does some malloc and many syscalls. You can zoom as much as you want to see what is your program doing. This was the beginning, but we can also zoom to another area. For example, wrong way. Okay, if you zoom at the beginning of just when the second thread starts to wait, you see that it does a read syscall, and then it waits. So it is waiting for data to arrive, and it blocks because this data is not available. And if you zoom at the end of this period, you see that the red syscall finishes, and it is because the second thread has produced data and makes it available via the write syscall. So this is a really simple example of a program that is not optimized. I do not recommend you to write such a program, but this is an example to show that tracing clearly shows where your bottlenecks are and makes it very easy to correct because you know where it comes from. This was a problem with a bottleneck, but it can be also used to see locking problems and many problems with very low cost. So if we summarize, tracing is to record events to use in a later analysis. So you want to say, I already have printf and printk and systemtap and ftrace and everything. So what is the difference with logging, for example? It's just recording events. I have printk. Actually, it's more, it's focused on performance in order to be very, not to be intrusive in the trace program execution. It achieves this by having a very compact binary trace format. In the case of LTTng, for example, it does buffering instead of writing directly to disk. It tries to avoid locks, have per CPU structures, and use RCU to avoid locks and avoid blocking, and does low-level optimization. The main difference with logging is an average 1,000 times faster using tracing with LTTng in this example. You can achieve a very, very fast trace point time. For example, here it's 200 nanoseconds per event, which is quite slow, quite fast. Many people trace. There are lots of users in various fields, from EV workload servers to intrusion detection and real-time, and especially embedded systems. Lots of users trace their products because it allows you to save resources like time and battery, many resources that are critical for embedded systems. And you can be a user since it's easy to set up and use. So we presented tracing, and if we summarize this part, tracing needs to be lightweight, fast, and efficient. The goal being to trace as much events as possible without altering the original execution. That's what we want to achieve. Lightweight, fast, and efficient. Now let's present the hardware we selected to achieve and meet these goals. Microchips are no longer just CPUs. You know it, it's been a long time now. You have floating point units, you have GPUs, you have DSPs, you have video processing units. You have lots of things, including debugging units and performance monitoring units. And in these units, you have tracing units. On almost every platform now have tracing units. ARM has its own. Freescales also, Intel, and there are lots of them. And we selected these 3 ones that are more adapted to event tracing than the others. STM and ETM are on ARM platforms, whereas BTS is on Intel x86 platform. These units are already supported by proprietary software. which is good software, but as you know, not easy to customize or use it for event tracing purpose. That's why we wanted to make it open source. Also, the tracing units I mentioned are widely spread. Do you have one of these? Personally, I have this one, and if you have one of these, then you have STM. And also, most newer ARM processors have ETM on it. So it's widely spread on the ARM platform. Same thing for Intel. Is your Intel CPU more recent than this one? I bet, unless you are a dinosaur. Then you have BTS on it. Okay, we have seen tracing. We have seen hardware. Now let's combine two and see how to use hardware to enhance tracing and how to use it. How to use it right. First, let's see STM. What is STM? STM is the system trace module. In newer versions, it's called system trace microcell. And its goal is to help software recording events. So it's perfect for event tracing. How does it work? It provides dedicated resources, like a buffer, and a timestamping unit. And you use it by instrumenting your software. That is to say, you modify your software to trigger events at the point you want to record this event. This is done by writing to a special address. And the hardware will take your packet and take care of it and timestamp it and store it to a dedicated buffer. This is summarized in this picture, where you see the CPU writes to the STM. Then the packet is timestamped, stored in the ETB, which is a buffer on board, on the system on chip, actually. And this data can be fetched later via the system bus. So this is easy to use.
You said this is on ARM?
Yes, this is on ARM.
What version of ARM does it start on? Like, is it on Cortex-A8 or is it on?
Actually, it's an ARM-based system on chips. It's not on the processor. It's on the system on chip.
So the SoC provider has to choose to put that in.
Exactly. For example, all OMAPs have it. And so we wrote open source libraries for using STM to trace events. This is where they are available. And we try to keep the same functionality as another tracer would, a software tracer. So we wanted something that is LTTng equivalent. So by using tracepoint in your code, you store an event through the STM, and you can even embed payload in your tracepoint, exactly like you could do with LTTng. And the consumer retrieves this, although you can send traces through a JTAG interface out of the chip, out of the board. But the only problem with this is that trace is encoded in STP, which is an optimized format. It's a really good format, but it's compact. The problem is it's proprietary. Documentation is not public, and neither it is a trivial format. So this is a problem. Though decoding is required to read the trace, so we had to study it and reverse engineering it to be able to decode it. It's not perfect, but it's just sad that it's not public. And here are the results, what we get in terms of performance. Here you see a comparison between a program traced, another one traced with LTTng, and another one traced with hardware using STM and ETB. It shows the time spent per trace point. The first benchmark here is a benchmark. It's just a loop running trace points, just to see the overhead of one trace point. And the other one adds a lot of computation just to simulate a real program. In real life, your program don't trace so often. So the overhead is really fewer than this. It's negligible. But here we wanted to make it under trace condition in order to show the difference. And what we see is that tracing with hardware is, in this benchmark, 4 times faster than a software tracer like LTTng. So we have good results. There's the thing we need to precise with LTTng. There's a part of the overhead that is due to two system calls. The first one is clock get time. It's used to get a timestamp to put in the packet and save the event date. And the second one is to get the CPU. And those two syscalls are not yet in VDSO for ARM. That's why they are so long and so big in this graphic. Maybe one day it will be in VDSO. I think clock get time is on its way to be in VDSO. So it will be even more faster. Okay, we have seen STM. Now let's have a look at ETM, which is also on ARM platforms. ETM is to the embedded trace microcell. It has been replaced in newer version by program trace microcell, but it's basically the same thing. Its goal is to trace execution. So it's not like STM. Here it's to trace execution, that is to say, save every executed instruction address and store it. How does it work? It provides dedicated resources also, like address comparators, buffer, and timestamping, like for STM. It can focus on a specific process or function. If you want to trace only one process in your system, or just one part of one code area, and you don't have to instrument your software, because the software doesn't have to know it is traced. What is going to happen is that ETM is bound to the CPU, and it listens to the bus and just sees what is going, for like instruction fetching and data fetching, and it can store events when it matches the condition defined with a process or function focus. Here you see the same graphic as previously. ETM is here, really bound to the CPU, and it will create events when it matches. The events are timestamped, and it is stored in the same buffer as STM. This is good for correlating traces. In the same way, you can fetch trace later via the system bus. So, as we said, ETM is not meant to trace events. So if we want to do event tracing, ETM needs to be hacked, and it needs to be used not in the way it was supposed to be. So our idea is to do execution tracing on event addresses. So when we know where we want to trace events, we just configure ETM to trigger at this addresses, and then it will program trace our program at the event address. So it's a hack, and that's what we did. So we wrote kernel support for to be able to focus on a process or a specific function. It was not done. So it's available. There's a link at the end of the presentation for the patch. And with this, you can easily trace in user space one other program and focus on a function or a process. Here are our results. It's the same representation as with STM. You see a program traced with LTTng and another one traced with hardware using ETM and ETB. And you can see that there is an amelioration. It can be faster with hardware. The problem is that with ETM, there is a limited number of trace points, since ETM has only a few address comparators, so you can define a limited number of points or events in your application. On the platform I had, it was three address comparators, so only 3 trace points. The other problem is that you cannot embed payload in your event, because it is not meant to. Now let's see what we can do with BTS, this time on Intel x86. BTS is the branch trace store module. Its goal is to trace execution like ETM, but it's not like ETM, as we are going to see. How does it work? It is in the CPU, and you can configure BTS to write events, to write every branch to an area you define in RAM. So once you have configured BTS, every branch is stored. Every branch is stored as a 24-byte record, and there is no compression, so it's a bit heavy. If you have, for example, a program that is doing 1 million branch per second, I let you do the math, but it's a lot of data. The main differences with ETM is that BTS does not provide dedicated buffers. It writes in RAM, and it cannot focus on a specific process or function. It traces everything. Every time you meet a branch, a call, a read, a jump, anything will be recorded. So this is the difference. BTS is already supported in the kernel with perf, but for execution tracing, for program tracing. If you want to taste it, you just have to do perf record, blah, 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 my program. It will record all this data in a file called perf.data, and then you can display it and see every branch your program have taken. This is very interesting for debug purposes, although it is heavy. It will slow down your program, slow down your program. So as we said, BTS is not meant to trace events. If you enable it, it will trace everything, and the ETM hack is not possible here. Still, we wanted to measure performance, so we ask ourselves the question, is tracing everything with hardware faster than tracing just events with software? Because it could be. Using hardware, you have dedicated resources. It can go faster. And if we can get every event recorded in a file faster than recording just events by software, we have the data we want. We have more, but we have it, so it could be interesting. So to answer this question, we did a test. This test that I'm going to present is just a loop that we are going to trace in one case by hardware with BTS and in the other case with LTTng. If you trace this loop with BTS, at the end of the loop, there's a branch to go back to the beginning, and this branch will be traced. So we are going to trace this, and on the LTTng, with the LTTng traced program, we just add the trace point before the branch. So we have two programs, one traced with hardware, the other with software. We have the same number of trace points recorded. The program does basically the same thing. That is to say nothing, but at least we are going to compare performance. And what we see is that using BTS, so hardware is slower than using a software tracer. It takes more time, so it's even for recording the same number of events. And we thought it was strange. Okay, LTTng is fast, but there is something strange because Intel says it is not supposed to be so slow. So we dived into Linux to see how it deals with BTS, and this is how it is currently implemented. In the original perf, each core is programmed to write to a dedicated small buffer, 64K. And once this buffer is full, or upon context switch, all this data is copied to another big buffer in user space. And then perf writes this data to a file stored on disk without the async flag, which means it can be copied another time to a system buffer. So here we see that we have one or two unnecessary copies from RAM to RAM, and one is done during an interrupt handler. So this is not good for performance, and we decided to re-implement this in a new feature called splice, because it does not go to user space. So this is a new feature that can be enabled by with an IOCTL. Here, the cores, if there's the small buffers are replaced by a big ring buffer composed of many sub-buffers, and every core is configured to write to one of these sub-buffers at the same time as previously. But the difference is when one is full, the core is configured to write to the next free one, and the full buffer is labeled to be emptied later by a kernel task when there is time. So once again, the patch is available. There's a link at the end. And by using this implementation, here is what we achieve. It's the blue bars. The overhead is reduced twice as compared to the original perf, and it becomes faster than software tracing. The different programs that you see here is they have different branching rates. It's an average on a Core i7. You see the average is like 5 million branch per second. So now let's look back at our results in this talk. With STM, we had a performance reduced 4 times as compared to LTTng UST. So it is a great improvement, and it needs to be looked at further. With ETM, we also have an improvement. But ETM, as we said, has a limited number of trace points because it has only a few comparators, address comparators, and you cannot embed payload. So it is not really meant to do tracing unless you have specific needs and you only have ETM on your platform. If it meets your needs, you can use it, but it's not comparable to a software tracer, a full software tracer. And BTS is not meant to do tracing, event tracing at all. It is not flexible enough. But we are going to see that there is new hardware coming on Intel. So don't trace events with BTS. Although, if you want to do execution tracing, you can use our patch, which gives a much better performance if you want the program trace. There are other hardware on other platforms. For example, Freescale has data acquisition messages, which is a feature similar to STM. You can save events by writing to a special area. Your messages will be timestamped, so it's good. Program trace is similar to ETM and BTS. It does execution tracing. The problem with this Freescale material is that it's not documented, at least not publicly. So we couldn't try them. Actually, we are currently negotiating with Freescale to get documentation, but you know how it is with jurists and everything. So we don't have any data or plots on this. And with Intel, there is processor trace, a new feature that is coming. It's not on silicon yet, at least not for us. I'm sure they have prototypes, but it will be released pretty soon, I think. I don't know if there are Intel guys in the room that can give us information on this. But it will give lots of features comparable to ETM to do program tracing, execution tracing, with filtering and triggering, lots of features and interesting things. So keep that in mind, and it will be interesting when it will be out. Wrong way again. Okay, a few words to conclude. Tracing is an easy tool to see under the hood, and it helps you solve your problems or simply improve your software performance, especially if you do embedded applications. It can be a very useful tool. LTTng is an easy using software tracer that can be used. It's packaged in every major distribution, including Yocto. So you just have to install it, and in a few commands you set up tracing, and you have trace data that you can analyze on another host and see it like we have seen on the beginning. And it has a low overhead. It is meant to do so. On ARM, as we have seen previously, it's 5 microseconds per event. On x86, it's 200 nanoseconds. And using hardware, you could achieve even less overhead. And I also encourage you to enable tracing in production, because most interesting bugs and features happen in production. And if tracing has almost no overhead, almost zero footprint, you can do this. These are a few links if you want to use LTTng or TMF or driver patches I mentioned before. And I thank you for attending this presentation. And I would be happy to answer questions. Yes?
ETM, that traces the program counter, as I understand. Is it possible to also trace writes to particular data areas? I want to see when I'm modifying.
Yes, with ETM you can, the question is it possible to trace something else than instructions? You can trace data that is coming, so you can trace read and write also. This is an interesting feature. Any other questions?
We support for giving you page logs, things like that.
Excuse me?
MMU activity.
This hardware, I don't think it does. Not the free ones I showed. Okay, thank you for your attention.